Okay, so today we will start looking at a new topic, which is equilibrium. Okay, now there are two types of when we're talking about equilibrium. Basically, we are referring to things which are not accelerating. Things which are not accelerating in terms of acceleration in a straight line. So the velocity of this particular object is not increasing. If the velocity increases, then there's acceleration, or this particular object is not rotating faster. Up to this point, we have been studying motion in straight line, and these recent weeks we have been studying motion in a circle, angular motion of an object moving in a straight line, and motion of an object moving in a circle, or something which is just rotating on its own axis. So what we have seen is that when it comes to things which are moving in a straight line, for the velocity to change, or basically for you to have acceleration, according to Newton's second law of motion, you need to have a net force. If you have a net force, and that net force which you have, according to Newton's second law of motion, is not equals to zero, then the particular object which is experiencing these forces is going to undergo an acceleration. So what am I trying to say? What I'm trying to say is that when there is equilibrium, there is no acceleration whatsoever, whether it's acceleration in a straight line or acceleration, angular acceleration, where some object is rotating faster and faster. So an object which is in equilibrium is going to remain at rest, or is going to start, it will be moving at constant velocity, or will just be rotating at the same angular velocity, or will not rotate at all. So what we are trying to answer really here is the question, why do objects remain at rest? Why do things move at the same speed? Or why do things rotate at the same speed? Or why do some objects just decide that we are not going to rotate at all? Are we clear? We have answered the question, why does the velocity of an object change? The reason why the velocity of an object changes is because there is a net force which is acting on this particular object, and the direction of the velocity in which the velocity is going to change is the same as the direction of the force. We have also answered the question, why do objects rotate? The reason why an object rotates is because there is a torque which is being applied on this particular object, and this torque causes this object to rotate. Are we clear? That is the reason why the velocity changes, an object undergoes acceleration. That is also the reason why an object rotates, because there is an applied torque. What we are trying to answer with this particular topic is, why is it that some objects, despite experiencing forces, some objects will decide, no, we're not going to move. We're just going to sit where we are. Some objects will decide to remain at rest. Other objects will decide to say they're going to move, but they're going to move at constant velocity. So, there are two types of equilibrium. There is equilibrium. Whenever there is equilibrium, so there are two types of equilibrium, and whenever equilibrium is there, the acceleration is equals to zero. That's the first thing. Equilibrium is associated with a condition under which objects experience zero acceleration. Now, an object can experience zero acceleration if it is at rest. So if an object is at rest and the velocity of this particular object is not changing, then we say that that particular object is in a state of static equilibrium. If an object, on the other hand, is experiencing zero acceleration, but this particular object is moving at constant velocity, then we say that that particular object is in a state of kinetic equilibrium. So there are two types of equilibrium. One, static equilibrium, which is associated with objects which are at rest. The other kind is kinetic equilibrium, which is associated with objects which are moving with constant velocity. Our focus in this course is mainly going to be on the first one, static equilibrium. we want to understand why do objects remain at rest? And if they remain at rest, how can we make sure that these particular objects remain to continue at rest? We are not only interested in making sure that this particular object does not move, but we also want to make sure that this particular object does not rotate. So when it comes to equilibrium, we want to make sure that the position of this particular object remains the same. If the position changes, it means that this particular object has moved. We also want to make sure that this particular object does not rotate. So to make sure that there is no rotation, what do we need to do? Is it clear what we want to do? What we want to explain? We want to explain why objects remain at rest and they continue to remain at rest. For example, if there's some stone outside your yard somewhere there, if no one decides to move that particular stone, it will remain there. So why is it remaining there? Okay? And also, there are certain things which tend to rotate, but they decide we're not going to rotate. What is the reason why they are refusing to rotate? So during the course of this particular lecture, we'll introduce you to what are called concurrent forces and also what are called planar forces. Then there's something called the first condition of static equilibrium. Now, and there's also something called the second condition of static equilibrium. Now, for you to have equilibrium of any sort, there are certain conditions which need to be met. One of them is what is referred to as the first condition of static equilibrium. The other one is what is referred to as the second condition of static equilibrium. The first condition of equilibrium is that the net force which is acting on this particular object has to be equal to 0. Basically, what we mean is that when you add up all the forces which are acting on a particular object in equilibrium, an object you are interested in, you are trying to find out why is this object not moving. When you add up all the forces along the x direction, along the y direction, you add up all these forces. What you need to meet, the condition you need to meet is that these forces along the x direction and along the y direction, they should add up to 0. That's the first condition of static equilibrium. You add up all the forces along the x direction, you add up all the forces along the y direction. If you want this particular object to not accelerate, to be at equilibrium, the first thing which needs to happen is that these particular forces, all of them along the x direction, the sum of the forces along the x direction, the sum of the forces along the y direction, they should add up to 0. When this condition is met, then the position of this particular object you're interested in will not change. If the position doesn't change, then we tend to say that the object is at rest. And if that if those forces continue to remain 0, then that particular object will continue to be at rest. So for an object to be at rest, you need to find out what forces are acting on this particular object. Along the x direction, you need to find out what forces are acting on this particular object along the y direction. Then you add up all these forces, and these forces need to add up to 0. If what you're interested is in making sure that that particular object remain at rest, and if that particular object has to continue being at rest. So that is the first condition of equilibrium. The second condition of equilibrium is that there should be no net torque. The net torque, when you add up all the torques, when you add up all these forces acting on this particular object, some of the forces acting on this particular object will cause this particular object to rotate. Some of these forces will not cause the object to rotate. So our interest in the second condition of static equilibrium is with those forces which tend to cause this particular object to rotate. We want to make sure that the amount of rotation these particular forces, these forces are causing in one direction which we sometimes tend to call the clockwise direction, the direction in which the arms of the clock move, meaning that this particular object, a force can cause an object to turn clockwise, and the other forces which are causing this particular object to turn anti-clockwise, if we add up the torques, then these torques have to be equals to 0. So we usually kind of choose to say clockwise torques are going to be positive, anti-clockwise torques are going to be negative. Then when you add up how much torque has been produced by the forces which are trying to make an object turn in a clockwise direction, and how much torque has been produced by the forces which are trying to cause an object to turn in an anti-clockwise direction, when you add this whole thing up, it should end up giving you a total torque which is equals to 0. Are we clear? Is it clear what we are trying to do? In a nutshell, that's what the topic is about. We are trying to make sure that things remain at rest, or we're trying to make sure that things do not rotate.
So I don't know if you can just repeat on what you were explaining about the torque being 0.
We need to make sure that the torque is 0. We need to add up all the forces, because there will be some forces which will cause this particular object to rotate. Some of them will not. So we need to look at each force. How much torque is this particular object, each force producing? If it's producing a force of a torque of 0, that's fine. We don't have to worry about that particular force. But there are some forces which produce a torque which is not equal to 0. And these forces producing a torque which is not equal to 0 will tend to rotate your object in a particular direction. So we need to find out what each and every torque force is doing in terms of torque. Then we make sure that the forces, the torques in a particular direction and the torques in the other direction, they are equal, so that when we add them, they end up being 0. Equal in terms of size, but torque is a vector. It has got direction. So if the torques are in opposite direction, in particular direction, for example, a clockwise direction, when I say that a torque is in a clockwise direction, I mean that this particular force and its resulting torque causes an object to rotate in a clockwise direction. Then you've got other forces whose torques are in an anti-clockwise direction, so they tend to cause an object to rotate in a different direction. Then those particular forces or torques, we're going to call them negative, or we're going to designate them as negative forces, negative torques. Okay. So the first thing which we need to agree on is something called a system of forces. So basically, a system of forces is just all the forces which are acting on a particular object. All the forces acting on a particular object, they could be acting in different ways. There is weight, there might be friction, there might be some applied forces here and there might be a reaction force. Basically, all the forces which are acting on a particular object in all the different ways in which these forces are acting, that is what is referred to as a system of force. For us to have what we need as equilibrium, these forces, when we add them up, all the forces, when you add them up, they need to give us a net force which is equal to 0. There are two types of forces. There's something called concurrent forces, then there's something called planar forces. Now, concurrent forces are forces whose line of action, when you talk about a force acts in a particular direction. The direction in which the force is acting, that is what is referred to as a line of action. Are we clear? A force has got size, and the force acts in a particular direction. The direction in which the force is acting, that is what is referred to as a line of action. So, since we have this thing called system of forces, which is a bunch of forces which are acting on a particular object, these forces can act through a common point. Their line of action can pass through a common point, if the lines of action of forces are passing through a common point, then these forces are called concurrent forces. On the other hand, if these forces don't pass through a common point, but they lie in the same plane. If you have got forces acting in the same plane like a piece of paper or whatever it is, like that, if you've got forces acting in such a manner that they lie in the same plane, then those forces are called coplanar forces. What we are going to be interested in mostly are going to be some coplanar forces. All our forces are going to be coplanar, but it's also possible that some of these forces might pass through some common point in which we are interested in. And some of these common points are basically what is referred to as a pivot or a center of gravity, SG. Okay, are we clear on the terminology, on what constitutes a concurrent force and what makes up a planar force? Concurrent forces are simply forces whose lines of action pass through a common point. Planar forces do not necessarily need to pass through a common point. The only requirement for planar forces is that these forces lie in the same plane. Are we clear? If I draw forces on a board, say, oh, this force is pointing in this direction, this force is pointing in this particular direction, this force is pointing in this particular direction, those forces I'm drawing on a board, on a white board or in a green board, whatever it is, those are coplanar forces, because all the forces I'm drawing on the board, they lie in the plane of the board. So if I draw a force on a board, it is a coplanar force. If you see a force drawn on a piece of paper, it is a coplanar force, because all the forces we are talking about, they lie in the same plane. If the forces you're talking about pass through, their lines of action pass through a common point, then we refer to such forces as concurrent forces. Are we clear?
Yes, sir.
Okay, so we move on. So what do we need? We have said that there are two types of equilibrium. There is what is called static equilibrium. There is also what is called kinetic equilibrium. In both cases of equilibrium, the acceleration has to be equal to 0. Whether we are talking about the acceleration A, the linear acceleration A being equal to 0, or whether you are talking about the angular acceleration being equal to 0, in both cases, the acceleration has to be equal to 0. Then the next thing is, if we are talking about an object which is at rest, an object whose position is not going to change, or an object which is not going to rotate, then we are talking about static equilibrium. On the other hand, if this particular object's position will change, or this particular object is going to rotate, whatever, especially if the position is going to change, then, but under the same, with no acceleration happening, moving with constant velocity, then we are going to say that there is what is referred to as kinetic equilibrium. Our interest in this course is in static equilibrium. Static equilibrium, which is caused by concurrent forces, forces which pass through a common point, and also coplanar forces, forces which are acting in the same plane. These forces should make sure that there is no acceleration which is happening. If there is no acceleration which is happening, then this particular object will remain at rest. The first condition of static equilibrium or equilibrium is that when you add up all the forces acting on this particular object, when you add up all the forces, and you have seen how to do this because forces are vectors. If you're thinking about a force being a vector, then it means that you have to identify which direction is going to be positive, which direction is going to be negative. So when you add up all these forces, they need to add up to 0. The reason why these forces add up to 0 is because they do not cause acceleration. The acceleration is equal to 0. For you to make sure that all the forces add up to 0, you need to identify which forces are acting along the x direction. You add them up. You need to identify which forces are acting along the y direction. You add them up. And when you add up all these forces acting along the x direction, you add up all these forces acting along the y direction, they should give you 0. So there should be no acceleration whatsoever along the x direction and along the y direction. This first condition of equilibrium is the one which explains Newton's first law of motion. The first law of motion says that an object will remain at rest and will continue to remain at rest, or an object which is moving with constant velocity will continue to move with constant velocity until it is acted upon by an external force. So if there is no external force, like in this case, since objects tend to be acted upon by a bunch of forces or system of forces, if you add up all the forces acting on this particular object, and these forces, they produce a total force, a net force, or a resultant force which is equals to 0, then in that case, there will be no acceleration. If there is no acceleration, it simply means that the position of this particular object, if it's at rest, will not change. Or if the object was moving with constant velocity, in which case we are talking about kinetic equilibrium, then the acceleration will not change, or the velocity of this particular object won't change. We are not talking about kinetic equilibrium in this case. What we are talking about is what we are talking about in this case is static equilibrium. So our interest is in making sure that we find out the reason why an object remains at rest by ensuring that there is no acceleration. Is that clear to everyone? So this is what's going to be the task. Always trying to make sure we identify forces, then we enforce these things. We make sure that all the forces acting along the x direction, they add up to 0. All the forces acting along the y direction, we add up to 0. We want to come up with this thing. We want to enforce this because that's the first thing we need to make sure that an object is at rest. Are we clear? Now, for us to do this addition of forces, like I've said, forces are vectors. You need to have a way in which you're going to say which direction is which. So the easiest way to do these things is if you follow the xy plane. The positive x-axis, we usually choose the positive x-axis to be a positive direction. So if the positive x-axis is positive, then the opposite of that is going to be the negative x-axis. We give it a negative sign. So any force pointing in the positive x direction, we give it a plus sign. It becomes a positive force. Any force pointing in the positive x direction, we give it a plus sign. Any force pointing in the negative x direction, we give it a minus sign. Similarly, any force which is pointing in the positive y direction is given a plus sign, and any force pointing in the negative y direction is given a negative sign. When you follow this convention, where a force pointing in the positive x direction is given a plus sign, a force pointing in the negative x direction is given a negative sign, a force pointing in the positive y direction is given a positive sign, any force pointing in the negative y direction is given a negative sign, we can do this. We can do the summation. This thing here means add. This is mathematics for summation, sum, to add things up. When you add our forces along the x direction, they will give us 0. When you add our forces along the y direction, they will give us 0 if we are interested in making sure that this particular object remains at rest. Are we clear? Are we clear?
Yes, sir.
The other thing which you need to do, there are certain things which you can do. You need to identify the object which needs to remain at rest. Sometimes it's not everything we want to remain at rest. You need to identify which objects am I asked to make sure remains at rest. It might be an object, it might be a position, it might be a point. But you need to find out, you need to know, you need to correctly identify which object is supposed to remain at rest. That's the first thing you need to do. Ability to identify which object should remain at rest. After you identify which particular object should remain at rest or should not move or should not rotate, whichever one it is, the second thing you need to do is you need to identify which forces are acting on this particular object. So you kind of like focus on this whatever object it is, then you start identifying what forces are acting on your object. You create something called the free body diagram, where a free body diagram is a lazy way of saying if you've got a car, you just draw a box. If you've got a human being, you don't have to draw a human being, you just draw a dot. So basically, when it comes to a free body diagram, whatever object it is you have, usually we tend to present the object with a big dot. Then on this particular big dot, you start showing us, oh, there is this particular force. So this force is pointing in this particular direction, and this is how much the force is. Are we clear? It doesn't matter whether it's a person you have identified who is supposed to remain at rest, or whether it's a box, or whether it's a car, whatever it is, or whether it's a cat, or whether it's a dog which is supposed to remain at rest. We are just going to represent whatever object is supposed to remain at rest with a big dot, or whatever it is you're supposed to use. You are comfortable with using maybe just a big dot, a big black dot. Then after that, you start identifying certain forces. Oh, this particular object must have weight, it must have mass. So if it has got mass, it must have weight. So the weight should be pointing down. Oh, it's on a floor. So if this particular object is on the floor, there must be a normal force pushing against this particular object. So the normal force should point up. Or this particular force trying to pull this tension, trying to pull this particular object in this direction. So the force should be in this particular direction. So you show us what forces are acting on this particular object. Okay, so you isolate the object of interest, then you create what is referred to as a free body diagram. Then on this free body diagram, you show us what forces, all the possible forces which are acting on this particular object. They're not going to be many, maybe there will be 4 or 5. Okay, then for each force which you identify, after you identify all the forces which are acting on this particular object, you will create a table of contents, a table of components. You create a table of components, and the components we're interested in here are the components of each force. So your particular table is going to have a column for the vector or the force. So then there's going to be another column for the x component of this particular force. There will be another column for the y component of this particular force. So for each force, you work out what is the x component of this force, what is the y component of this force. A component is simply how much a particular force is in a particular direction. Are we clear? So for force number 1, how much is this force in a particular direction? Force number 2, how much is this force in a particular direction? And remember, when you're doing components, you need angles. The angles a force makes has to be measured from the positive x-axis in an anticlockwise direction. Once you find the components for each of the forces which are on your free body diagram, then you start writing out the first condition of equilibrium. Basically, what you're saying here is, when you see this, you add the x components of the forces. After you add the x component of the forces, you have to make sure that the x components of these forces, each of the forces you've identified, has to be equals to 0. You also add the y component of the forces. When you add this y component of the forces, they have to be equals to 0. It does not matter whether you know how much a particular force is or you don't. If you do not know how much a particular force is, then you just write fx. Force number 1 x, force number 1 y, f1x, f2x, if you do not know how much a particular force is. Because sometimes you will not know, and we are asking you to find out a particular force which is not known. So basically, these are the steps you follow when trying to enforce the first condition of static equilibrium. You need to identify the objects which needs to be in equilibrium, or the object which needs to remain at rest. Once you identify that particular object, then you can draw a big dot. Then you need to represent that particular object. We are not very interested in the detail. Then you need, on this particular big dot, you need to start showing us which particular forces are acting on this particular object and in which direction these forces are acting. After you do that, the third thing you're supposed to do is you are supposed to create a table of components where you're going to put the x components and the y components of each of the forces which you have identified to be acting on this particular isolated object. After you do that, you write out your condition of static equilibrium. And you make sure that the sum of all the x components is equals to 0, the sum of all the y components is equals to 0. Then you work out which forces you're supposed to find. Usually there will be a force which you're going to ask you. There will be a force which you will be asked to find out and stuff like that. So that is what is needed for you to make sure that a particular object remains at rest. The other thing which you are interested in is making sure that these things do not rotate. We want to make sure that an object does not rotate in any way. The reason is because if it rotates, then it means that there is torque. If there is torque, then this particular object has got moment of inertia, and if there is moment of inertia, we are saying this particular object, since it's rotating, it has got angular acceleration. If something has got acceleration, then it is not at equilibrium. So we need to make sure that as much as there could be forces acting on this particular object, since there's nothing we can do about these forces do not cause this particular object to rotate. So, if you have got a force acting on a particular object, these forces will usually tend to produce a turning effect, which is what is referred to as a torque anyway. Now, torque is not just about how much turning effect a particular force is producing. Torque also has to do with the direction in which this particular object is going to turn as a result of this particular force. So torque is a vector. There is how much turning is going to happen. That is the size of the torque. There is also the direction in which this particular object is going to turn as a result of this particular force. That's the direction part. So if you have got how much the size of the turning effect, if it's a large turning effect, if it's a small turning effect, we don't really care. As long as there's a turning effect, then there's a torque. Then we talk about, okay, fine, this particular object is going to turn in this particular direction. If it's going to turn in a clockwise direction, that's okay. If it's going to turn in an anti-clockwise direction, that's also fine. So there's direction. That means that torque is a vector. Now, what we normally tend to do is that we tend to choose torques which are in a clockwise direction to be positive and torques which are in an anti-clockwise direction to be negative. That's up to you. Usually for most people it works just fine. If you are unhappy with that, you can decide to choose to say, I'm going to choose anti-clockwise to be positive, then I'll choose clockwise to be negative. But whatever you choose, when you choose it, then you stick to it. Are we clear? You can't change your choice of direction in the middle. Okay, you can't change your choice of direction in the middle. And this is just a reminder of how we work out the torque. The size of the torque, or the amount of turning effect, the torque is equals to the force multiplied by the distance between the point of rotation and the point of application, which is the R, then multiplied by the sine of the angle between the direction, the line of action of the force, and the direction, the distance, and this distance R from the point of application of the pivot or the rotation point to where the force is being applied, which is theta. So this is how we find out how much turning effect is there. So this bit here, tau is equals to FR sine theta. this gives us the size of the turning effect. This gives us the size of the turning effect. The direction of the turning effect can either be clockwise or anti-clockwise, depending on whatever is happening or depending on how this particular force is acting. If you choose clockwise, if something turns clockwise, then you say it's going to be clockwise, it's positive, that's fine. Then if it's clockwise, it's positive, then it means anti-clockwise is going to be negative. If you choose anti-clockwise to be positive, then it means clockwise is going to be negative. The other thing which you might need to be aware of is this particular term, r sine theta. This r sine theta is also what is referred to as a lever arm. R sine theta is a lever arm. It's very, very important. Lever arm is defined as the perpendicular distance from the pivot to the line of action of the force. Very, very important. The distance from the pivot to the line of action of the force. When from the pivot, you draw a straight line. This straight line should meet the line of action of the force at 90 degrees. You draw a straight line from the pivot, and this straight line should meet the line of action of your force at 90 degrees. How much the length of this straight line you're going to draw from the pivot which meets the line of action of the force at 90 degrees, that is what is referred to as a lever arm and is represented by this bit here, r sine theta. Do we have a diagram somewhere which we can use to explain this idea of lever arm? No. Okay, fine. Okay. So we'll basically, Okay. So that's basically about what torque is, and this whole thing about lever arm. Okay. The other thing is, the sign convention of the torques. Like I've said, a force can produce a torque which will cause an object to rotate in a clockwise direction, or a force can cause a torque which will cause an object to rotate in a counterclockwise direction. Whatever it is, you have to choose, since you're dealing with a vector, which direction is going to be positive and which direction is going to be negative. If you choose clockwise to be negative or positive, then any particular force which causes a turning effect in that particular direction is going to have a torque which is negative. If you choose the other one to be positive, then any particular torque which causes, any particular force which causes a torque in that particular direction is going to be chosen, is going to produce what's referred to as a negative torque or positive torque, whatever it is you choose. The other idea which needs to come to your attention, which we need to bring to your attention, is the idea of an axis of rotation or a pivot. Now, you need to choose if things are going to rotate. If something is rotating, then there has to be a center about which this thing is rotating. Are we clear? Sometimes the pivot can be obvious to say, obviously this is the pivot, this is the center where, for example, when you have a wheel attached to a car, clearly the pivot or the center of axis of rotation is very obvious in such a case. In other cases, it is not so obvious. In such a case which is not so obvious, the pivot or the axis of rotation can just be chosen arbitrarily. However, what you need to know is that if the line of action of a force is passing through a pivot, that particular force will not produce a torque. This is the thing you need to know. If you are going to choose a pivot arbitrarily anyway, what you need to take advantage of the fact is that if you have got a force, then this force line of action passes through the pivot. It means that in that particular case, this R is going to be equals to 0. This arrow which you have here, the arrow we have here is going to be equals to 0 because the force is passing through the pivot. If the force passes through a pivot, then arrow is equals to 0, then it means that whatever the force multiplied by 0 multiplied by whatever this angle is, that is going to give you a torque which is equals to 0. Which is a good thing. It's a nice thing to have a torque which is equals to 0, because once you have torques, a bunch of torques, which are forces which are producing 0 torque, then your calculations become much easier. However, if you make a poor choice, since you have said that when it's not obvious what the pivot is supposed to be, you are just supposed to choose. If you make a poor choice of pivot, it means that you're going to have a lot of forces producing torques. If these forces produce torques, it means that you will have more calculations to do of trying to find out how much is the torque, how much is this torque, how much is that torque, and stuff like that. So when you are choosing a pivot, choose a point on this particular object which we are trying to make sure does not rotate. When you are choosing a pivot, choose a point on this particular object you are trying to make sure does not rotate, where a lot of forces are passing through. A number of forces are concurrent, where the line of action of these particular forces are passing through. If you choose a point where the majority of forces are passing through as your pivot, then it means that all those forces which are passing through that particular point will not produce any torque. If they do not produce any torque, then that's good for business, because you're going to have very little to worry about. Maybe you're just going to have 1 or 2 forces to worry about because you made a very good choice of pivot or axis of rotation. Are we clear on what the plan is? What are we planning on doing? It will become very obvious when we start doing the problems, because after this, as you have seen in your notes, there is a whole lot of questions, examples. So this whole message which you're trying to put out here will become reinforced. We want you to understand why we will be doing things the way we'll be doing them. Okay. So, a choice of pivot. Sometimes a pivot you can just choose. A pivot can be any point. However, axis of rotation depends on how the particular object is shaped and whatever it is the particular object is doing. Okay. What does it say here? Any particular unknown forces exert 0 torque if they pass through a pivot and therefore does not appear in the torque equation. Yes. So this is basically the big idea here. If you have got a force, you choose a pivot nicely, then your force passes through the pivot, then that particular force will not produce any torque. Excuse me, just a bit. Someone wants to... Maybe? Yes, how are you? Yes. You want to teach people? Okay. Yes. Okay, there is another thing called center of gravity. Center of gravity, also called center of mass, is simply a point on an object where the mass of this particular object is concentrated. When you have an object, there is this point in this particular, whatever object you have, where the mass of this particular object is concentrated. For example, for our planet Earth, as big as it is, the mass of the Earth is concentrated in its center. If you have got some other kind of object, whether it's a flat object, whatever it is, there is a point where you can balance this particular object so that it doesn't fall off like that. That particular point is that's what's referred to as the center of mass or a center of gravity. Okay, that's all I have to say about that particular bit. We will not need it very much. What we're going to need in our problem solving is a pivot, and also you trying to make a good choice of what a pivot is. What would make a good pivot? Okay. Now, the other condition which is required for you to make sure an object does not rotate is the following. As I've said, there will be a bunch of forces acting on your object. Now, when these forces are acting on your object, most likely what is going to happen is that these forces will turn your object by a certain amount in one direction or another. So what I'm trying to say is that the forces acting on your object will try to rotate your object in a particular direction by a certain amount. If a number of forces try to turn your object in a clockwise direction, then we are going to refer to such forces as producing a clockwise torque. If you have got a bunch of forces trying to turn your object in an anti-clockwise direction, then we are going to refer to such forces as producing an anti-clockwise torque. So whatever forces these are, we are going to try to add them. We're going to try to add all the anti-clockwise torques. We're also going we're going to try to add all the clockwise torques, and we're also going to try to add all the anti-clockwise torques. When we do this addition of clockwise torques and anti-clockwise torques, what we are hoping to get is that at the end of the day, the torque should be equal to 0. Only if the torque is equal to 0, the sum of the torques, once we add the clockwise torques, we add the anti-clockwise torques, only if the sum is equal to 0, only then can we make sure that this particular object does not rotate. So, with the second condition of equilibrium, we are trying to make sure that this particular object does not rotate. Even if it's in the same place, we want to make sure that it doesn't rotate. With the first condition of equilibrium, we are trying to make sure that this particular object remains at rest. It does not change its position. So in this particular case, since we have said torque is a vector, you have to choose. If you want to choose, or say, clockwise torque to be positive, then any clockwise torque, force producing a clockwise torque, will treat that as a positive torque. Then the other ones, we're going to treat them as negative torques, so that when you add them, they all add up to 0. When they do that, then our object will not rotate. Are we clear?
Sir.
Yes.
So, let's say, for example, you have chosen that the anti-clockwise is, let me say, negative, and then the clockwise is positive. So meaning all the torques that you'll be getting from the clockwise will be positive, and the anti-clockwise will be negative.
Yes, you give them negative signs. The other ones you give them positive signs, the other ones you give them negative signs.
Oh, so that when you add them, they'll give you 0.
Yeah, we have to make sure that when you add them, they give us 0.
Okay. Thank you very much. Huh?
All right. Again, there is also another set of tricks which you can apply with respect to the second condition of equilibrium. In that, the first thing you're supposed to do when you're trying to apply this condition of equilibrium is that you need to identify which particular object we are trying to make sure does not rotate. So you need to correctly identify the object we are trying to make sure does not rotate. Once you identify that particular object, you can create a free body diagram of that particular object. Then on this particular free body diagram, you indicate which forces are acting on this particular object we are trying to make sure it doesn't rotate. Once you indicate the direction of the forces, then the other thing you're going to do is you try to identify in which direction will this force try to cause this object to turn. If the force is passing through your pivot, then that particular force clearly will not produce any torque. This is a very, very important point. Note that all forces whose line of action pass through the pivot does not produce a torque. So if you choose a pivot, because you are trying to make sure that this thing doesn't rotate. So if it's going to rotate or doesn't rotate, there has to be, whether it rotates or does not rotate, there has to be a pivot somewhere. And you can just choose a pivot to be any point. But you need to take advantage of certain things when you're choosing a pivot. You need to choose a pivot where a number of forces are passing through, because if those forces pass through that particular pivot, those forces will not produce any torque. So what we are saying is, you identify the force, you show us the direction of the force, then you mark which force is going to cause a clockwise torque, which one is going to cause an anti-clockwise torque, by seeing the most likely direction in which this particular object is going to turn as a result of this force. Then once you do that, you write out the sum of all the forces, which will be the clockwise torques. You do this. You write out this thing. The summation of the torques, which will be the clockwise torques. You add up all your clockwise torques. This force will produce a clockwise torque. This one plus this one plus this one plus this one plus this one. You add them up. Remember, by this time you have already decided to say, oh, clockwise, I'll take clockwise to be positive, or I'll take anti-clockwise to be negative. You've already decided that. Then you identify which torques are anti-clockwise, so you add them up. So you come up with a sum of all the clockwise torques. You come up with the sum of all the anti-clockwise torques. This bit here also doesn't care whether for a particular force you know how much it is or not. It doesn't really matter. You can still work out what the expression for the torque is supposed to be. Then after that, you carry out this thing. You add your clockwise torque plus your anti-clockwise torque. Then you make sure that your clockwise torque plus anti-clockwise torque must be equals to 0. Once you do that, then you find out what kind of quantities are you being asked to solve for. So you're going to come up with some equations. Using these equations, hopefully you will be able to find whatever quantities we are asking you to find out. Okay, so when we meet next week, we're going to start with example number 1. Any questions on what is a plan? Any questions on what the plan is? Of course, some of these things, as you can see, this is a very, very long thing. Try to go through it, because I've tried to explain as much as I could what's going on. Okay, you see a lot of explanation, so it's not that you are left with nothing. So between now and next week, I have tried to explain things. It took a lot of time to type this stuff out, but we have tried to explain as much as we can as possible. Okay, so that when we meet next week, if you are lost somewhere, at least you have a good idea of what it is we are trying to do. Any questions?
So I have a question.
Yes.
When finding the sum of the anti-clockwise and the clockwise direction,
Clockwise torques.
is it possible for the torques to have same signs?
No, they can't have same signs. Why should they have same signs? You have said that you're going to choose. If you choose clockwise to be positive, then anti-clockwise becomes negative. If you choose anti-clockwise to be positive, then clockwise becomes negative. So why should they have the same sign? They can't have the same sign. You have to make that choice. Say, when it turns this direction, it's going to be a positive torque. When it turns the other direction, it's going to be negative. If you choose one direction to be positive, it means the other direction is going to be negative. Any other question? Huh? Yes.
This is not already on the motor.
Ati? Yes, they're already there on Moodle.
This note.
Yes, they are there on Moodle. The notes are there on Moodle. So go on Moodle, look, you find the notes, download them, print them, study, so that you can understand what's going on. Any other question? Okay, so if there are no other questions, it's 15 hours. We come to the end. See you next week on Monday when you start looking at the problems.